Let's see. It goes from about
what about
oops. Okay, so we got through the part where we were doing S as a function of time, and we went to erase that. We were at the point where we were doing S as a function of time, velocity as a function of time, and then acceleration as a function of time. And we realized in order to go this direction, we need to take a differential. In this direction, we need to integrate. So let me go through and catch us up on the actual sections we're on, so that at least, you know, since you paid for the thing and since you have to, it's probably a good idea to go in and read it. Now let me show you what he does in here. And he makes it kind of nice because each of the sections, like he's got an example here, like 5 examples here. And then he goes down here, and you'll notice each of the sections. What you'll notice about the sections, there's not a lot to read there. So if you look at this first one, here I'm gonna have to look on this screen. You'll see that it's really not that much. So this is actually one of the larger sections, but fortunately, you've already seen this kind of stuff. So you go through it. If you go down here to section, okay, give it a second. 12.3, give it a second here. You'll see this is the part on erratic motion, which is basically the recognition of the 2 diagrams. Hey, it's kind of, wait a minute, how do I do this? Is that a little bit better? Can you see a little bit better? And those lights act weird all of a sudden. I don't know what to do to. I don't know what that does. What about this button? Oh. Okay, I don't know what that does. So what you'll notice, oh, I made them flash. Okay, how do you get rid of them completely? Oh gosh. Oh, there we go, got rid of them. So, you know, this is basically what we talked about the other day, but you'll notice he goes in, kind of talks a little bit about it, you know, talks about integrating. Oh, and we need to talk about this too. This is something that's interesting that comes about. Let's go ahead and do that. That was something I did not purposely skip. I just forgot. So you realize that, okay, this only applies in the connection between the velocity and the acceleration. It doesn't occur here. It occurs in this section. So here it's this part. So you realize, and you knew this before you came in, that the change of the velocity, you know, with respect to time is equal to acceleration. That's great. But let me give you a scenario where you're kind of caught and you don't have that. Let's say you go over and you have seen, all of you have seen the wind tunnel over there, right? I mean, at some point. You may not have messed with it yet, but you'll get to mess with it later. So it's big up here, shrinks down, and it's got a little glass section. Usually this is, I think ours is 18 inches, and this is 40. I can't remember if it was 48 or 45. I knew it at one time, but I know that's 18. So what happens is, you turn the thing on, and way over here is the fan, and it's basically sucking air through there. And if you go in here and look at it, and you stare at a particle, Here, let me kind of accentuate I'm going to kind of zoom in on this part. Make it kind of more, you'll see why in a second. So let's say you're staring, so here you are, your eyes are staring at this spot. And so you stare at that spot, you stare at it over and over. Maybe you stick a probe out there at it. Maybe you do something like that. So somehow you're staring at it and the velocity is equal to 10. But what you notice is it doesn't change. This function of time is equal to 10. So your first inclination would be, oh, it's not changing with respect to time, right? So dv dt is equal to 0, right? Actually, that's not correct. And this is the part that delineates between what you're seeing here and what you'll see in a fluid mechanics setting. Almost exclusively, I've never seen an exception to this rule, but I'm sure you can if you look hard enough. People in fluids stare at a thing and see the velocity. And what did I say? It's 10. So it's 10 here. What do you think it's up here? Is it higher than 10 or lower than 10 or equal to 10? Just your gut reaction. So if you get a bunch of people in a crowd and they're all like this and you say fire and there's a little exit, how fast do you think the people go here versus back here? They're going faster. They're getting the crap out of there. So this is the same thing. It's a mass flow. Turns out that's what happens here. Think of this as so let's just make it up. I'm going to make even numbers for myself because I can, I don't want to waste the time with weird numbers. So I'm going to say back here it's 5. Maybe I'll make this 15 because I want to make it equal in the difference, and you'll see why in a second. So the people back here, nobody's hollered fire. You got up here, people are hollering fire, and then everybody's trying to get out the little neck down entry or exit to get out of there. But that's not what we're looking at here. Okay, all of this that we've talked about is sit on particle. What I mean by that is you're sitting on the particle, riding the horse. So you're essentially, everybody here is in wherever it's at, somebody hollers fire. You're all sitting on a horse, and the horse, here you are, and you're basically tracking the horse. Or you're on the horse, you're tracking yourself. So essentially, these are parametric, meaning that S is given only as a function of t. Over here, you're staring at something, and particles are passing you. So they're coming by. You have to look before, and you have to look after to figure out, well, did before it go slower or faster? And after did it go slower or faster? And so you look around it. Well, how do you do it mathematically? Well, you recognize, as this guy right here recognized, he recognized that he has the velocity as a function of, and I'll just say it right now, x and y. He's staring at a particular x and y location. Well, back here, you only have s, so so let's measure s this way. So here's s going this way. So he's just measuring s at that particular spot. Well, now how do you take the derivative of that with respect to time? So let's just make something up. Velocity is equal to, I'll put an equation on it. 10 plus 3s. And what I'll do is I'll say my s, this is s equals 0. Back here is s is equal or less than 0. And over here, s is greater than 0. So my axis, if I looked at it, I would say here's s, happens to be v is equal to, what did I say, 10? And then over here, say s is equal to 1. that the velocity was equal to 15, back over here, s is equal to minus 1, over here, s equal to minus 1, you have the velocity equal to, what I said, 5. So essentially look back to the left, look to the right. I don't know that I actually have that. Actually, I do have that if I put in a 5. Okay, so if I look at s of 1, put in s equal to 1 here, I get 15. Put in s equal minus 1, I get that minus 5, and it knocks it down to 5. So this is the equation that matches what this guy observed here. So the question is, how do you find that? Well, it turns out, if you want to do this, here, I'll write it down. This is the same thing as this. It's that chain rule thing. So you don't have v as a function of t, but you do have it as a function. You do have it as a function of s, and you have this. So it turns out this, if you stare at it long enough, and actually you don't have, it doesn't matter how long you stare at it, it still is always the velocity. So what you get is the equation that looks like this. Oh, sorry. So if you wanted to find the acceleration at, say, s equal to 0, what you do is you take this, equals to 10 plus 5s, times the derivative of that thing with respect to s, which gives you nothing more than 5. And if you put in s equals 0 there, you're going to get an acceleration of 50. So even though the guy sits there and stares at this and sees that the thing doesn't change with respect to time, he can't conclude that it isn't accelerating, because he is looking at, it's what's called Eulerian. Man, I'm goofed that up. This is called Lagrangian. It's the frame of reference. Here, you're sitting on the particle. All these are parametrics, and they're basic, and we'll get into parametrics by the time we get done, because this also is in parabolic motion, is all parametrically written. And over here, he's looking at it from the Eulerian standpoint. He's standing there staring at a puddle of water as it flows by him. He's not tracking every single particle. That's harder to do, is track every single particle anyway. Actually, I'm not even sure that it's really all that much possible anyway. So, so it's just a simple breakdown of this. So essentially, you've got this one particular situation that, here, I'll put it right back up here, where the acceleration is equal to the change in velocity with respect to a position. And usually it doesn't matter whether you put the velocity in front or back, but for some reason they tend to put the velocity in front of this, and that's okay. And I think the reason they do is because they can bring the ds over. So this equation will get you this equals to v dv. The nice feature is this, okay? So you can start integrating. And this is the part where you've got to match the bottom and you might match the top. So if you were going to say velocity at S1, and this is going to be S1, and this is going to be S2, and the velocity at S2. So in fact, if I had this, wait a minute, where did it go? Oh, I'm sorry, here it is right here. So if I had this, or I had the acceleration of 50, and I stuck this 50 in, it doesn't have to be 50, it's just so happened it came out to be 50. But if I stuck that in at 50, what I'd end up with out here on the other side is I'd end up with, what's that, v squared over 2 evaluated, oops, oh, okay, sorry. At velocity at S2 and velocity at S1. And if I put in a 50, don't I get 50s? Is that right? Well, okay. let me rephrase that. If I put in 50, I get 50s and S1 and S2. So here's the problem on my problem, is I have to know an S1 and S2. Of course I do. I know a 5 and I know a 10. I'm sorry, I know a 5, I know a 10, and I know a 15. I know 3 places. So the key is when I saw this, I was like, uh-oh, I forgot that. And so the key is this 1/2 V1 squared minus V2 squared actually is that. I've got mine this way. This term is this one. That term is this one. If you are given acceleration as a function of s, you just take off and integrate the thing. But then what you do is you set it equal to these two terms. And that's the only difference. You have something weird over here. That's the only thing that's different. So does that kind of make sense? I should have filled that in. It was, we pretty much used all our time last time that I remember. So maybe maybe it's okay that I left it off. But does this make sense? I mean, it's just a change in variables. And I don't know very often, except in satellites, rockets, cannons. Okay, so if you're looking at satellites, rockets, same thing, cannon, those are the situations that you're generally tracking the particle as a function of time. Water, airflow, aerodynamics, anything to do with flowing water, it's usually looked at this way. It's usually looked at where you, like the wind tunnel, you make part of it clear, and you stare at a spot, and you watch this stuff come by. So there's a filling one. Okay, wait a minute. I never check and make sure. I like to check and make sure the stream started, and I also need to check. Yeah, there's audio. Looks like it's going. It did not send me a notice this time. Why am I not connecting to the network here? There I am. So I don't know. I have no idea why I'm not connecting to the network. But I see myself there. Okay. So these are the VS and AS graphs. So it's harder to do. It's harder to give this and get this than it is to do this and get that. Well, I should not say that because some people may find one of them easier than the other. So I'll take that back. So it's the same concept. Then you're essentially done. And he's got some videos in here. So what I'm trying to get at is the sections are not that long to read. And when you read them, you don't really have to understand them exactly the first time you read them. Just read them, go down. He gives you lots of video stuff in here. And actually, there is, is it the study area? I think there's an area that has, video solutions, GeoGebra. This is kind of cool. I use this a lot. Free body diagram. But here it is. So what am I saying? So there's all sorts of video solutions in here. So if you're like, I don't get that, you just go in there and look at that. Now, unfortunately, or fortunately, some of the videos are repeated in here that are in the text. So just be aware of that. But let's go down to the next one, which is general curvilinear motion. Let it come up, and then I might make it go away. So general curvilinear motion, he's got a bunch of stuff in there. He goes through it, but let's just lay it out in a quicker fashion that he has. Because that's, I think, one of the duties I'm supposed to do, is there's a lot of text on the screen, but mine is to simplify it down so when you glance over and read it, it reads very quickly. So curvilinear motion means, I got a vector, I got some x. I'm going to use x and y right now, but later on I'll use another coordinate system. So if you have a vector out here r, guess what? It's nothing more than xi plus yj, right? So now you want to know the velocity. See, the particle is going like this. So it's doing like that. Okay, so maybe it's going that way. So it turns out the velocity is tangent to the particle path. So the velocity vector, which that's a vector, is nothing more than the rate of change of this. And he's got all this stuff in the drawings and talks a little about it. But my duty is to just lay it out very simply, so when you go back, you can maybe see, he's saying this or that. So when you do this, he has one section here. This part is, I'm going to put a box around because you may be sitting there thinking, why is he doing this? But I'll tell you why that is in a second. So if you're taking the derivative of these terms with respect to time, you're going to have dx dti plus x times di dt. Now, you may be saying, what? But I'll explain that after I write the other two. dy dt j plus y times dj dt. From a mathematician's viewpoint, that's totally correct. A mathematician who's just isn't told what the physical ramifications of x and I is, that's what he's going to do. But then the question is what is that? And you know, you have your I vector here and your j vector here. They're all of length 1. They sit there and point there, and they stay there. They're not pointing or changing. So in fact, this term is 0. Now, why would I even write that? Now, I'm going to give you, go ahead and show you why you write that, and then we'll address it later. So the reason you write that is because here's somebody else who loves polar coordinates. And he says, I hate x and y coordinates. I want to write that r vector as simply this. And he said, okay, hang on. It is true, there still is an x and y, but what he has decided is he wants to use the base vectors like this and like this. Now we'll get to this soon enough, so I'm not really. So it is true, there's an I and there's a j. However, when he reaches the next stage where he says dr dt, okay, just a blind mathematician would do this, and he would say dr dt ur plus r times dur dt. Now this time, the change of this base vector, it does change with respect to time. And that's the reason he talks about, he says this, he talks about this for 5 seconds or maybe less. In the text, he displays it and say it's done. He doesn't tell you significantly why he did it to begin with. But the reason he did it to begin with is because later he's going to have this. So here's what happens, okay? So here's this. Say this is maybe 5. Okay, let's just make up a case in point where this is maybe 3 and then this is 4. If that's 3 and 4, then that's 5. You know, it's just the distance from this point to that one. That's that. It's a scalar. And this is the direction. And so that's the UR. But guess what? Say maybe 10 seconds later, it's over here. And there's theta, and guess what? There's U theta, and there's UR. So in fact, this vector did not change in length, but it did change in direction. And because of that, that's why he talks about these. Now, as long as you understand that concept, we will go in and address and drive all this maybe, I don't know, we're not coming here on Monday. So maybe Friday, I don't know. I have no idea. Maybe the next Monday, I don't know. So now that we've got that, does that kind of make sense? I'm just laying it out so you see where it is eventually. So right now, you don't need either one of those terms. So what you have, x dot I, and by the way, I've had this question before, what's the x? So x dot, or anything, any variable, p dot, I'm just making anything, is basically this, where p is any variable. Could be r, could be this symbol, could be that symbol, who knows? It doesn't matter what it is. Now, in math also you had y prime, or you had z prime, or something like that. Well, that's nothing more than z with a spatial coordinate. So if it's a prime, it has a spatial coordinate. If it's a dot, it has a time coordinate. That's all that it is. So essentially this and this are the same thing, plus y dot j. Now, somewhere in the book he may also say this, the velocity in the x direction plus the velocity in the y direction. These are equivalent. So these are equivalent. All those are the same thing. And then the last thing is, obviously I don't even have to do this too much except to say dvx dt plus dvy dt j, or you could write it acceleration in the x I plus acceleration in the y j. So really, everything you've done before, you just work. Now the x and y are kind of independent. So if you had, let's just say, let's come up with one. Just going to make one up. X is equal to 3t plus 1. And y is equal to 7t plus 5. That's going to be pretty boring. But you look at this thing, this means x dot is equal to 3. Y dot is equal to 7. X double dot, guess what x double dot is? Okay. X dot is equal to this. X double dot is equal to 2 of these. Or, well, I can just leave it at that. So this is the term that is the acceleration in the x direction. Well, if I take a derivative of that, I get nothing. Y double dot is going to be acceleration of y is equal to nothing. So if you look at this, the r vector, which will be 3t plus 1 I plus 7t plus 5 j, the velocity is going to be nothing more than 3i plus 7j, and the acceleration is going to be 0i plus 0j. So you just take that, take its derivative, run down, take its derivative, run down, and you're done. Or you can take this and integrate it going up, So why would you want to do that? Well, okay, now I'm going to have to scroll down because I'm not sure where he starts doing it. Okay, obviously not this section. Okay, I push that button. Here he is. Okay, so he included the z as well. Okay, forgive me for not including the z. It's essentially nothing more than another coordinate that just is, you do the same thing to. So what you'll find, well, that's not an image. The velocities look the same way. Oh, I can't get that to zoom in. Nothing fancy. Why would you do this? Because you want to do motion of a projectile. So in a motion of a projectile, usually, okay, here we go. It came out. Usually, it's written in an independent form, meaning you have an x equation, you have a y equation, but it can be put together. Hang on. So the first thing that's assumed is the acceleration always goes in the opposite direction of the y. When you took physics, I'm guessing that was the case. I don't know. I haven't I guess modern physics isn't really that modern, depending on what your time frame is. So you start throwing the thing out there or shooting it, it follows a parabola. The equations are further down, and so what he has is the horizontal motion and the vertical motion. So what he comes up with is the fact that, okay, so what he decides is, and this is true, g is equal to a constant. And so therefore the acceleration is equal to a constant. If you've got an acceleration that's a constant, that's kind of nice, because if you have some sort of acceleration that's a constant, okay, let me do it this way. dv dt is equal to acceleration, which that gets you this. And you can say, I'm going to say v naught, t naught, v and t. But if I put in just a constant, I get a c, and then I get a t. I should have made this c. It's a constant value times a t evaluated from t and t0. What he does throughout here is he assumes that you're shooting your cannon, you're throwing your ball, whatever, where you start your stopwatch the minute somebody shoots the trigger to launch the thing. So throughout all this, he assumes that. If that's the case, then that's pretty easy, because this is going to be just acceleration over here. Then what you're going to get out of this is v minus v naught. And you're going to say, well, velocity is equal to v naught plus, because I moved this over to the right hand side, acceleration is ct. So what I'm going to do is I'm going to just sort of put this up here. I don't know what to do for the first, so I'll just say acceleration constant is equal to minus g. The acceleration is constant is equal to minus g, then velocity is equal to v naught minus gt. Okay, now this is assuming we're going in the y direction. The next thing I'll do is I'll rephrase this and say, well, dy dt is equal to the velocity. Now, first thing I should do is I should say this, and I really don't have to do anything to that. Take the dt over, integrate it. I'm going from times 0, and then I leave that there, dy, y naught, and y. And so what this will come up with, I'll take this and stick it in here. So give me a second. So what I'll have is y minus y naught is equal to the integration from 0 to t of that thing, dt. So I get nothing more than vy naught t minus gt squared over 2. All that's evaluated from here to here. And so the right-hand side just becomes vy naught t minus gt squared over 2. And so now I'll make a little space underneath here. Oops, sorry. Y is equal to y naught, because I take, I take this minus y naught, move it to the right-hand side, so it becomes plus, of course. And then I get vy naught t minus gt squared over 2. This is the set of equations for the y. And so what you'll see is this same thing. It's kind of hard to see. Okay, so here he's done the x. It doesn't really matter. If I do the x, I just replace y with x. I said that, and I didn't do that. X naught. But there is no acceleration. There is no g in the x direction. So I just have that. And then, I have a t. And then I have vx is just equal to vx naught. And acceleration in the x direction is equal to nothing. So essentially you get two somewhat, they look to be somewhat independent, if that makes sense. But they are kind of dependent, but in a strange sort of way. So I wear this hat because it's hot. It gets my head hot. Now it doesn't do any good. So here he did the horizontal motion. Here he did the vertical. He's got to put these in a blue box somewhere. Okay, wait a minute. Let me keep going down. There's got to be in a box together, isn't it? No, I guess not. Okay, so I guess, and if you zoom in, oh wait, what happens if I do that? Okay, so here we go. I mean, this last one is back to this thing where we know the velocity at a certain location. So I didn't write that one down. We can go back and look at that one later, but right now let's focus on these two. This is the one that's here. It just so happens the constant acceleration becomes minus g. And somewhere down here he's got the, oh, I'm sorry, take that back. It's right here. So he puts in AC of minus g, and he gets this set. So this set of equations minus that one is the one I've got right here. Then this is the one for x. So what, you've seen these before. So what in fact is new here? And to answer that question, here's another thing. He shows this in the regular book. Let me see if I can find. No, that's just an example. Anyway, in the other book, what he did is he had two pictures side by side. One in which there was a tennis ball that he just pulled the thing out from under and it started dropping. And he did a strobe on it, kind of looked like that. Okay, then he had another tennis ball that he shot off here. And it did a strobe here. And it turns out it looked like this. So when it strobed, these were at the same elevation, even though on the board I'm not doing a good job of that. So these are at the same elevation. So what happens is you shoot the ball off to the right. It didn't look like I shot it very far, but it becomes a parabola or part of a parabola. This one just drops straight. But if we do a strobe and you do this, you'll find that they follow exactly that pattern. So what happens is this means they're kind of independent. In other words, this motion, this direction, is of course in the y. And the y equations didn't matter what my initial velocity is. So this one may say Vx naught is equal to 5. I'm just making up here. Vx naught here equals 0. So there never was motion in the x direction, where this is the x direction and this is the y direction. So this ball, tennis ball, had no motion in the x. This one had what? A constant velocity. So what happened is it just click, click, click to the right. So it just headed to the right. This, and I tried to draw it reasonable. So what happens is when you first drop it, it goes slow and then goes faster. So the distance between each strobe is a little bit longer. And you can kind of see that maybe in that last picture, but now I've already moved past that. So in essence, the two equations are actually independent. To get them, put them together is where you get the parabolic motion. And so let's just do an example, and then I'll show you what he does differently here than what you do in physics. Oh shoot, I don't have a whole lot of time. Well, let me just say, you've seen parabolic motion, right? So it's not anything new. let me just tell you what is going to be new and different here. And I'll just lay it out, and then we'll work some like Wednesday. So you shoot a cannon, right? In physics, what they were trying to get you to do is, what's the total height of the ball, or whatever it is, the cannon, how far did it go? And they were happy asking you that. So here, they're going to say, okay, the guy is a baseball player. He hits a home run, but the stands are out here at usually, how about 400 feet? And the stands are at an angle of usually, I don't know, how about 45 degrees. And where did it land at out here? So who got to catch the ball? Sometimes it can go over the stadium, sometimes it doesn't. But the difference is this. If you recognize this is a parabola, and then you recognize this is a straight line, and then what you do is you remove everything else, and you're back in math, and now you're looking for the two locations that these 2 points cross. You'll get two solutions. One is no. You'll get a number, you'll get an X, and you'll get a Y. I mean, and it'll be based upon, I shouldn't erase that. You'll get an X and a Y, but you'll also get this one. And this is the one that your solution is looking for. And yes, and once you get this, you'll get X equal to, I'm making stuff up, 512, and Y equals to 50. And from there, you can figure out how far it is up here, things like that. Essentially, this is the additional part, is where if you want to get complex targets, you want to find out some interesting things, usually it boils down to, doesn't have to be a straight line, most of the time it is. Straight line and a parabola that's turned upside down, and you'll get the equations out of it. You just solve those two. That's it. Now let me come back to one other thing, and that's parametric. The word parametric. Okay, so if you look at this thing, I have that, right? I stick in 1 second, I get the Y. And guess what? So if I stick in t is equal to 1 second, I have to stick it in this equation, stick it in that equation. That's what's meant by parametric. There's a parameter that's common to both of these that you have to put that in order to find it, where X is, and you have to find where Y is. That'll be crucial for us to break apart that parametric view in order to get that curve, and I'll show you how to do that. It's actually very, very simple. Once you do it once, it's the same procedure every single time. There's nothing really new or different about it. The only time you might be thrown a curve is when they put the coordinate system somewhere weird. More time than not, I like to put the coordinate system's origin where the cannon is, or where the football player is, or where the baseball player is. So, you know.
There's a question actually on homework like this. It's we're given a position equation, and it's telling us to find the total distance traveled.
Total distance of the football, baseball, whatever?
Yeah, like the absolute value, not the actual disposition.
Oh, okay. Well, I guess I'd have to look at that one, but the distance traveled. Okay, so there's two ways to interpret that. One is, okay, so this is, does it have a football stadium or something? Here, okay, let's take a look at it.
That's all it shows us, and that's for the total distance traveled.
Oh, okay. Okay, so that's a little bit different. Let me show you. Can you tell me those numbers when I get back up there?
Yeah.
That's slightly different. Okay. And that's a very good question. Okay. Okay, tell me what the numbers are. S is equal to
2t squared minus 8t plus x.
Plus x.
plus 6.
Oh, plus 6. As I
At
say,
t.
I'm now really confused.
At t is equal to 3.
At t is equal to 3.
Yeah, find the
Here's what you got to do. Okay, so because there's a minus sign in here, there is a possibility that if you plotted this, and the particle might go one direction and then reverse itself. Does that make sense?
Yeah, you get if you plug that in, it's just 0.
Yeah. So what you got to do, believe it or not, what I would do, okay, it kind of depends on which one you want to do, but you can plot S versus T. So as you go out on T, it must go like this, right? I'm guessing it might go the other way. And so, I know it sounds weird. Now you can do it. It's very complicated to take the derivative of this and find that, and then once you find the derivative, you can find the position, or you can just plot the thing. And then you zoom in here and say, let's just make this, I'm just making this up. Let's say this is 4 units, whatever that is.
Why is it concaving down?
Because I drew it wrong.
Oh, okay.
Yeah, it has to do that the other way. But anyway, you get my point. If it's just a parabola, either way it's going, even if it's going there, okay, that's a bad drawing. So it went down a certain distance and then returned. And so all you're doing is you're trying to find how far did it go that direction, and just multiply it times 2, and that's what it is. Does that make sense? Because it went there and then it returned back. Now that's given the fact. Wait, at 3. So if you put in 3 here, is this equal to 0?
Yeah.
Okay, so this is 3 and this is 0. So somewhere it went out there and it came back. So sometimes in the book he'll show, take the derivative and do all this. But to me, a picture's worth 1,000 words. So just plot the thing, look at it for a second, and say, okay, it went out there that far, it came back, we're done.
So did we just find the area?
Well, if you found the area, you'd find the velocity, but oh no, you wouldn't. Sorry, take that back. I don't know what the area would get you, but you could find the area if you wanted to.
No, I'm good.
How about that for useful and useless answer at the same time? So yeah, if you take the integration, that's not the. Sorry, I shouldn't have said that. Okay, so this was somewhat like, because it was parabolic, but it wasn't parabolic motion. So, but hey, anytime you're doing the thing, just ask me a question like that, I'll answer it.
I tried the derivative way, and I couldn't. So I went to kinematics, and I didn't finish. So.
Oh, really?
Yeah.
Yeah, I mean, you can do that, take the derivative and figure out where it's at, and the 0, and find the t, and go back and do it, but
Yeah.